Hey guys, Mr. Bouchard here, and we're here to talk about sound today. Alright, so this is notes 12.2 sound. So how does sound travel through a medium? Alright, and you may ask, what is a medium? Well, basically a medium in terms of science, this is actually a phase of matter. Alright, that's another fancy term for that. So whether it be a solid, a liquid, or a gas. So obviously some materials transmit sound better than others, and you may ask, why is that guy putting his ear to a railroad track? Well, from a distance, you can actually hear a train through the metal on the track faster than the air, right? Because sound will travel faster through metal material. Because the particles in it are much closer together. So we're going to get to that in a moment, a little more in depth. Also, what's happening with this shark and dolphin? Well, if you know a little bit about dolphins, they use something called sonar. Sonar is a form of like radar, and what they do is they basically send out a signal, and they're able to bounce it off of objects and know how far they are from that object. So that they use that actually against things like sharks. Sharks are actually hunting them a lot of times, so they'll use their sonar to know how far they are away, make judgments, and be able to change direction quickly to avoid them. So neat little trick using sound. There is a video here. I encourage you guys to watch it. It's actually a really good song by Metallica, played on the guitar, but they did a little neat trick. All right, they put actually a phone inside the guitar, and you'll actually see the vibrations in the string. All right, so sound transmits in waves, and that truly shows it. So watch that video. It is really cool. All right, it's a good song. Nothing else matters. All right. What is sound? Sound is a form of mechanical energy formed by a vibrating object. Sound needs a medium to travel through a solid, liquid, or gas. So one thing that's true, outer space, which has no solid, liquid, or gas material, does not transmit sound. So any movie where they show an explosion in space and you hear a sound with it, technically you wouldn't hear a sound because it does not transmit through the vacuum of space. So sound does not travel through a vacuum because there's no medium, there's no particles of matter for the sound to transmit or vibrate through. So they have to be present for that to happen. One experiment that demonstrates this, which I have a video later in the notes, which is called an evacuated bell jar experiment. All right, in this experiment, they hooked this up to a pump. They sucked the air out of the jar, and in doing so, there's no medium for sound to travel, and you will not hear sound. So I think they do it with a cell phone. They also sometimes do that with just like a bell ringing, and obviously when there's no air in the jar, you will not hear the sound. When they put the air back in the jar, you'll hear the sound again. All right, so pretty neat. You can watch that video later on. Okay, so sound waves speed depends on the density of the material in which it travels through. Okay, so you guys know a little bit about solids, liquids, gases. Solids, the particles are close together. They're very dense. So the molecules are close together, so immediately they'll contact each other and transmit the sound faster. So metal there in the rails will transmit the sound much faster than gases. Gases have the particles all spread apart, just bouncing around, which means sound travels slowest through gases. And the liquids are kind of an in-between, right? You may have done this in the pool, right? Even just speaking very lowly in a pool, you can actually hear the sound transmit all the way across the pool. All right, so you can play around with that and experiment that when things get warmer, all right, out and you get to go in your pools again. All right, but that's pretty neat. Okay, so here's an example of the speeds. So this is at 25 degrees Celsius. They decided to take the same temp and measure the speed of sound. All right, so iron obviously wins 5,200 meters per second. Glass is a close second at 45 340 meters per second. Water is a liquid that 1,497 meters per second. So you can see it's not as fast as a solid, but it's still pretty fast compared to air, which air sound travels at 346 meters per second. Okay, so again, you can see the big difference between each medium. Definitely much faster in solids than gases. Okay, also temperature. So those that are musicians, you know this. When the temperature is warmer, the waves can move faster. All right, and that's why you have to warm up your instrument before you start tuning it or playing it. Because initially, when you start blowing in the cold instrument, the sound will actually not sound right. It will actually be flat. So being flat is because the waves are moving slower through the instrument, and then as you warm it up, they start moving faster, and then you want to finally tune your instrument to make sure it sounds good. All right, elasticity also, the more elastic material, the slower the waves can move because it will absorb some of the sound. And then less elastic, stiffer, will actually make the waves move faster. So they do this trick with like auditoriums and things like that, or rooms where they want it to be dampened. They'll actually use elastic materials to sometimes dampen sound, and then sometimes use less elastic material to make sound bounce. Because auditorium is designed to make sound actually go towards the audience. So they use paneling in a different way to actually divert the sound towards the audience. Okay, measuring waves of sound. We use something called amplitude. Amplitude is the height of the wave from the equilibrium point. So equilibrium point is if the wave isn't even vibrating at all. So obviously a higher amplitude sound is going to be louder, and a lower amplitude sound is going to be softer. All right, that's measured in decibels. So those that do audio stuff may know that already. All right, but that's the units for that. Okay, frequency also is used for music. That's the number of waves passing a certain point. This determines the pitch of sound, or for those that are in music, determines the note that you're playing. So higher frequency, the more waves, the higher the pitch, or the higher the note on the scale. The lower the frequency, the less waves that are hitting an object each second, so the lower the pitch of the sound. Okay, so that also determines, like some instruments are more higher pitched than others, right? So the higher pitched instruments will have a higher frequency of sound in general. Okay, some other things about sound that you need to know. Sound and echo is sound that's reflected off objects. Light travels faster than sound. All right, you guys know that with lightning. All right, you see the lightning flash, and then you hear the thunder that follows. Right, because the thunder is actually the result of the lightning hitting the ground. Sound travels fastest through solids, slowest through gases. And a reminder of the types of waves. So transverse waves travel at right angles to the wave movement, look like an S. So sound usually travels in this way. Longitudinal waves travel in the same direction the wave movement. And we talked about that in the last set of notes. All right, waves do not have mass also. They are a form of energy. So it's not something that directly you can measure the mass of. It's something that's transferred from one object to the next. And again, you need a medium for this to happen. So the evacuated bell jar experiment, the example is here. You guys can actually watch that. And that's pretty much that. All right, so thank you guys for tuning in, and I'll catch you next time.